we get to have Mr. Jim Florwick join us again. Jim, thank you so much for participating with us today. Just if you do not know Jim, Jim has over 35 years of experience in design, integration, and maintenance of wired and wireless networks. Jim is a part of the Cisco team and was part of the Cognio acquisition in 2007. At Cisco, Jim is focused on radio resource management and Wi-Fi product development, and presently focuses on high client density network design and implementation. Jim, thank you so much for joining us today.
Yeah, so this has been outstanding today, and it's just kind of been a common theme. Loved what Chuck and Matt had to say about the future, and my heart just goes out. George, thanks so much for mentioning Spectrum. You know that I'm a huge fan of that, given my background. So I wanted to start with like a brief history of Wi-Fi spectrum, because it's a very disjointed journey on how we got where we are now. And this kind of leads into why Wi-Fi 6 to me is such a huge thing. And I think I'm going to probably echo probably a few things that have been said already, but let me see if I can't put a new slant on it. We started off with 802.11b, and then we got 802.11a at the same time. But at the time, 5 gigahertz was rather unachievable. Mostly because of power constraints. We couldn't get enough power to the amplifiers to make it transmit nearly as far as 2.4 gigahertz. All of those things, as they do, get better with time. And then up at about 2009, and I heard Matt mention this, we got 802.11n, and I remember that very, very well because I was getting killed on 802.11a trying to provide any coverage for conventions or conferences. And it was awkward because I was standing at the front of the room trying to tell people how wonderful Wi-Fi was, and they couldn't connect to email sitting in a room with one of my APs. But we didn't have a whole lot of choice then. 802.11n really gave us a boost. It gave us 450 megabits per second, which was a quantum leap over what we had. Also gave us 40 megahertz channels. And about the same time or just before that, we got Uni 2E. So we were going to use those channels. And then we got a little thing that we all learned about called the top terminal Doppler weather radar, which took 3 chunks out of it. And notice how that also took out a 40 megahertz channel. But we were still kind of waiting for 802.11n to really trickle in at that point in time. We also, at the same time, got Wi-Fi 5 right about then, which gave us an 80 megahertz channel possibility that we hadn't had before. And then we got Wi-Fi 5 release 2, which gave us 160 megahertz channel capability, which would have been great if you could have put 160 megahertz anywhere. And then 2018, we get 8 spatial streams and, 5+ gigabit connections possible out of the technology and the standard. And the only problem with this is to touch any of that or get anywhere close to it, you absolutely need an 80 or 160 megahertz channel. And the problem with that is there's just no place to put them. And that has been what's been holding us back, it seems like forever. And in fact, I do a brisk business in changing people's infrastructure from 80 back to 40, and I'll take all the accolades. It does seem to straighten things out. So just because I got a few fun files laying around here, this is back in 2008, and this was actually at a large hospital system. And I just completed talking to some folks, and of course they were talking about 2.4 gigahertz, which was trashed and was the bane of most of our existence in those days. But talking about 2.4 gigahertz, they were, clamoring, when are we going to get more spectrum? Because they got that it was crowded and they didn't have enough bandwidth. And I pulled a scan of their environment, and Uni 1, Uni 2, which was brand new then, and Uni 3 actually had no Wi-Fi in it at all. In this environment. In fact, Uni 3 looks like it might have one over to the right, but it's so distant it was just barely even there or registering. They did have a bunch of 2.4 stepping on top of each other. They did what a lot of people did in those days. They tried to sneak one in channel 3 and put another one up in channel 7 and see if they couldn't pack the band a little better, but we all know that that ends poorly. By contrast, this is 2018. So we went from a completely empty span of frequencies to what, at least from this wonderful shot of the spectrum that we were just talking about from Ekahau, shows quite a few APs on the same channel, and they're at very, very even powers. Now, this is a very high density keynote area, actually, but it really illustrates the problem. And here we are in 20 megahertz. We're in 20 megahertz channels because we have to be. We can't get separated with antennas and everything else that we're doing and counting on the people underneath them. We can't do it at 40 megahertz. We simply run out of channels and we end up with problems. So the question came up here about a year ago, I guess. How dense is too dense? And this was just before 2020 really got into its full-on swing. And I was able to be out in our test area. We've got a lab out in Richfield, Ohio, and it's got a lot of open space in it. It's got some walled offices. It's got cube farms. So it's pretty much like an open office area environment. And I was hearing things back, and I'm sure you guys hear it all the time. People saying, "Oh, I've got 200 megahertz cells," or 200 square foot cells. And I'm getting asked these questions, and of course, you don't want to tell anybody they put too many APs in, but they put too many APs in because a lot of this I got to sort out and literally move it around because they're just too close. But we got asked to provide some data, and we took the opportunity to do this. We've got 15,000 square feet, and somebody was wondering why we couldn't do 80 megahertz channels, at 1,000 square feet. I figured probably was the worst. And at the time, we were telling everybody 2,500 square feet, and we were telling everybody 2,500 square feet because if you did 2,500 square feet for a cell, 280 square meters, pretty much anybody could implement that. They could set channels, 40, which is probably our best practice right now, 80 if they were really not dense. But if they got down to 2,500 square foot, it would survive. It would actually do okay. So, when you get to say one thing, you try to hand somebody something that's not loaded and going to give them a real problem. But the reality is, 1,500 square feet, 1,200 square feet, this gets done all the time. Again, the reality comes down to the channels we have available. And around the world, that varies quite a bit, which means that the user experience is different around the world. And I know I'm not talking to anybody here who doesn't know this. But it makes a difference. And when you talk to people about that, it's almost like saying you can't have a dozen, but you can have 12, and somebody doesn't get the math on that. Running out of channels is a really common thing. People simply don't think about it. And it's exasperated now. We've got dual 5 gigahertz APs because capacity means putting more cells on the same square foot. You don't get bandwidth without an AP or a radio. So we took a look first at 80 megahertz. I was pretty sure we were going to explode this, and we did. I mean, and the math on this is pretty straightforward. How many 80 megahertz channels do you have? How many interfaces need a channel? And the ratio of 2.5 times of channel reuse with internal antennas means they're going to hear each other. And they certainly did. The image to the right just shows, channels 52 and 140 with just the 5 APs that chose that. But all in all, we had 10 co-channel neighbors. We had 10 APs that had to pick channels that were right on top of each other. And this is in 1,500 square feet. So it's not a big place. TX power was as low as it could go. Co-channel interference was very high. We didn't even bother doing any testing in here. You could just take a look at the neighbor relations and tell that this was going to be a complete meltdown. We did do testing at 1,200 square feet, which is supportable. In fact, that's even supportable with great care in European areas. And the reduced channels there, well, actually, you're getting more channels, but we'll talk about that later. If I did this with 6 gigahertz, if I did this with the FCC's version of 6 gigahertz, and you can actually do this with 5 and 6 gigahertz together, this results in not a problem. I mean, it quite literally can be done very easily, and that's the point. It fixes so much to have more spectrum. So we did some fun testing. We contrived a use case. We said, what would it be like if we had 8K video to support on a single AP? How much could we do? We did 40 megahertz channels because that's really what we were focused on at the time with 5 gigahertz. And we were able to support very nicely 8 clients that we reasoned should be at 80 megabits per second or better for 8K. And of course, that's a variable number, but 80 megahertz seemed like a good guess. And we were able to really get some nice throughput and performance with Wi-Fi 6. Throughput totaled out at about 780 megabits per second, which gave almost 100 megabits per second per client. And that's a good magic number because virtual reality at about 2K is going to stream at 100 megabits per second. And we've got that being deployed out there. So looking at this data, it's certainly doable. And one would expect if you went to 80 megahertz, you would be able to double that. And I've got some data on that a little bit later too. But then the question came up because people wondered, is co-channel interference, why is that a problem? Well, I mean, if you do this and you're into radios, you can't talk at the same time another radio is talking. Otherwise, neither one of you is going to hear each other. We are starting to get smarter about that. But this is still Wi-Fi 6. It's still 5 gigahertz. And if I took 2 of the APs at 40 megahertz that were close enough to hear one another, and we picked the middle one. I think one was at minus 52 and another one was at like minus 71 or something, but we picked minus 64. So that's a good solid overlap between 2 APs on the same channel. And we ran the same test. We ran 8 clients to each one of those APs. And what surprised me out of this is what really happened to the latency. But the throughput dropped by more than half of what you'd expect. And then the latency took a tank. That was almost 4 times worse. I was under 50 milliseconds for a one-way trip. So this is definitely going to produce an environment where you've got a very variable user experience. You can take a look at the throughput lines down there. And some people are just going to be dropped out of the system altogether. This is not going to be a happy day if you're the admin on this network. That's a fact. Now, the reality of this is, unless both of those cells are being driven hard, you're not going to see this. But that also leads to why this is such a frustrating problem, because it is literally a sometime problem, as most physical layer issues are. They come and they go, and they're conditional, and nobody sees the conditions. They just see the frozen screen or the fact that they couldn't roam, or the fact that they did roam and the experience went bad, but they're not aware of it. So this is the root of a lot of evil in a lot of places. So what we posited, and we had to come up with some recommendations because we had a lot of people saying, hey, well, we're doing it all day long. We're doing it all day long just means that you haven't overused the channel yet. And that's out there. I'm a seasoned admin. I don't like to leave things out there like that, but there's environments where this is perfectly appropriate for. Density requires channels to separate it. If you can't isolate the AP, you're not going to get the full bandwidth. So our recommendation at the time was, if you're going to do 1,000 square feet, you need to have some real skill to do that. You need to have a clear-cut design. You're going to need to have the ability to isolate those APs using the surroundings. And you can probably do this in 40 megahertz in the US, where you got the most channels, and probably not anywhere else. If you're willing to back up to 1,200 square feet or 1,500 square feet, if that'll support your use case, and in a lot of cases it will for most folks, then you can do that at 40 megahertz in FCC and ETSI. In ETSI, again, you're going to need some care in doing it. And the design part of this is really important. And I know you guys all know that. After you've done the design and you've placed the APs, they're the only thing that's not going to move on that network. Everything else is going to move around it, and it's going to change its patterns. And I think we've all been there when somebody says, oh, no, we're never going to put people over there. And then the next thing you know, you get a call. They've been in there for 2 weeks. The network's been horrible, and it's all your fault. So moving up to Wi-Fi 6, if I test on 80 megahertz, I'm very much able to blow the 1 gig barrier today. And it's not hard to do. And this is even before we get to Wi-Fi 6E. This is just an AP that we're firing up 2 interfaces on. So I can already go over 2 gigabits per second. if you'd have asked me before we took this data whether there was a need for a multi-gig switch port, I'd have told you no. I mean, my experience going back, we just don't see that kind of traffic being driven. Now, given the fact that we can, well, I heard somebody say it earlier. I always say bandwidth is like money. The more you get, the more you spend. And, when you think you can't use it up, go back to that 5 gigahertz spectrum that I showed you, because that took less than 10 years to get like that. It was probably like that from 2017 on or 2016 on. So the speeds are definitely out there. But in order to take advantage of that, we absolutely have to use 80 megahertz cells. And in a mixed environment without 80 megahertz cells, well, in any environment without 80 megahertz cells, you're just not going to get above a gig. I don't believe you can do it on 40 megahertz. That might change. We might gain some efficiencies with B, but we can't. The other thing, 6 gigahertz comes along. We get that in April 2020, literally some of the only good news we had in 2020, I think. And it was very slow. April 2020 was the announcement by the FCC. Now, immediately other people jumped on the bandwagon, started studying it. And as Chuck said this morning, the adoption on this changes literally daily, with Canada actually jumping in last night. So 6E is coming. When I first presented on 6E, it was last April, actually. I got a whole bunch of comments from folks that weren't in the United States wondering why they cared. And they quit not caring probably within months of that airing. So this is really happening, and it's really important to us, and it's really important to delivering the promise of Wi-Fi. And the most beautiful part about this is, since Wi-Fi's inception, and if you look at the track of our spectrum being handed to us, we were proving ourselves the whole way with this little experiment the FCC called open radio and non-licensed use. So as we go down through this, you can't bridge discontiguous segments. You can't, there were so many things. If you look at Wi-Fi and 5 gigahertz, it was adequate. It was what we had, but it certainly was not done on purpose. And when I look at 6 gigahertz, this was actually done on purpose. This was done with a good understanding. And as Chuck and Matt both mentioned, it was a group of industry specialists, and you'd be surprised how often they all sit together and have a beer, because it's a rising tide floats all boats, as we say. So we needed spectrum. We needed the ability to branch out. That little effort has exploded across the world. With last night, I got the notification on Canada dropping in. Now, there's 2 models out there. There is basically the FCC model, and then there's the ETSI model, which is being adopted or looked at in most locations, and both are fine. Look, I'll tell you what, 100 more megahertz of spectrum is priceless if you need it. 500 megahertz more spectrum is outstanding. 1200 megahertz spectrum, I venture to say, but I will probably see the day where we run out of spectrum there as well. We seem to be gobbling it up at a faster rate, particularly now since it's very effective. But there's a lot going on around the world right now on a daily basis. Now, each of these regions that have adopted, they've adopted similar channel plans, but things like standard power and the low power indoors and all of those things, those are changing by region. They're all putting their little touch on it. For instance, we in the US for low power have a PSD of 5 megahertz or 5 dB per megahertz. And Europe, I think, just came in with 11 dBm per megahertz, if not higher. So they've got a higher power, but I don't think we need it right now. One of the biggest problems of using wider channels, and I heard this mentioned earlier, was the noise, right? So we had a fixed power output that we were allowed to produce in 5 gigahertz and Wi-Fi up to this point. In 6 gigahertz, they addressed that by going to this PSD, right? Or power spectral density, which is basically saying the wider you get, the more power you can actually put into it, which is good because your signal to noise ratio drops by 3 dB every time you double a channel width, which is why 80 megahertz was actually very impractical. And I think probably, I don't know if anybody ever tried implementing 160 megahertz anywhere besides a lab, but it doesn't fit very well anywhere. And by the time you get to there, you've got 3 doublings. You're already down 6 dB on your SNR. So it's it's something we couldn't get over. Along with the space to put it in, the noise killed us. If we take a look at how 6 gigahertz is structured with that power spectral density, and I'm strictly looking at FCC here, because right now I believe it's probably the lowest power spectral density. Every time we double a channel, I get 3 dB to offset that. So looking at a 20 megahertz channel, if I go to 40 megahertz, I get 3 dB more to my AP's max EIRP, and my client can operate at 6 dB less than the max EIRP of the AP that it's connected to. So what does all that mean? What that means is if you take a look at your infrastructure today in a carpeted office space, I'm going to leave warehouses out of this, but in a carpeted office space, your APs are probably sitting there somewhere between 8 and 11 dBm, depending on the density. And most of the 5 gigahertz clients out there are going to operate max between 10 and 12 dBm, and we do just fine with that today, as long as we keep the APs separate. So I've heard a lot of people say low power is not going to do anybody any good. And then they get concerned about, the propagation or the fade path. Now, don't get confused by this. I used Ekahau to mark up a couple of things. And we don't have 6 gigahertz yet, but I went and had one of my engineers help me through the math of plotting the path loss, because I got it wrong twice. The third time I had it right, but I didn't know which one was right at that point. It looks like from the top of Uni 2 E, on the left, well, not the top, somewhere in the middle. If I look at a max EIRP of 23 dBm, which is what I'm limited to, 80 megahertz cost me 6 dB of signal to noise ratio. In 6 gigahertz in Uni 5, I'm really only losing 1 dB more in path loss. It's a negligible loss. And if I plot that out, and I take that 1 dB out of it and I adjust my power to make up the difference, which I did, you get the same area of coverage. So low power indoors is going to be a thing, and it's going to be a savior of a thing. Now, before you get too excited, what that means is that we can actually start treating 80 like it's the new 20 in 6 gigahertz. Indoors, I think we're going to be just fine with that. Outdoors, they just did a study all the way up Amtrak's corridor on the East Coast, and there wasn't one place that they couldn't find 80 megahertz of spectrum to operate in. So that's good news, and that's going up. If you've ever been up the East Coast of the U.S. through New Jersey and New York, that's a pretty densely populated area with a lot of microwave repeaters. So that bodes very well for standard power. A little perspective. When we ushered in 802.11ax, we were doing a thing called Mobile World Congress on a regular basis. And we had the luxury of looking at AC, not AX, AC, as year over year, we saw the attendance stay fairly static. The users were the same types of users, but we were able to actually gauge what the penetration into the market for AC was. And we think it was a pretty good model. I didn't include 2012 and 2013 because I remember 2012 Cisco Live, it was about 7%, and most of them were owned by us. 2013, we saw it was a little better. It was like 11%. But then it really started to take off in 2014, which is kind of my point, because by the time you get the density out there, there is a time lag in the market. So if we look at the time scale on 6E right now, what we're looking at is 2021, we saw the EU spectrum open up. We've got Wi-Fi 6E consumer APs out there. We've got a couple of devices that so far have got a 6E chipset in them. But reality is we're going to start shipping into the market last part of 2021, first part of 2022. And typically that means we're probably at least 6 to 8 months away, not saying you won't have a project, but 6 to 8 months away before the market really starts to adopt. Keep in mind, like Uni 2E, this is a new spectrum, right? So people are going to have to get devices in their hands. I do think it's going quicker. I can't prove it for AX because as soon as we got AX out to the field, we quit gathering in mass anywhere we could measure this from. So looking at the number of devices that are out there, and I heard it mentioned earlier, it's about 50% of the shipping market. I think we've got some time before 6E crushes us, which is good because it's new. What you should be thinking about at this point in time, and not just because I work for a manufacturer that sells switches, is when we put a 6 gig interface on that AP, we're going to stay under 30 watts. We're going to stay under 30 watts. We don't want to go over that. It's not going to go down with an extra radio. I promise you that. And immediately when you put a 6 gigahertz radio on there, you're going to be starting to support 80 megahertz channels. Arguably, it will be some time before you have the density. But if you take a look at this comparison between what happens on a multi-gig switch port versus a single gig switch port, and this is with 15 clients on 5 gigahertz and 3, I think, on 2.4 gigahertz. Yeah, that's it down on the bottom there. The throughput basically cuts in half, right? The latency stayed same, but this is a switch that's sitting in a lab. There's really nothing else going on it. So it's going to cost you performance. If you don't have 30 watts in place, that's going to cause you grief. And if it doesn't cause you grief now, it's going to cause you grief. So start thinking about these things. With Wi-Fi 6E, more is more better. And I thank you guys for being here today. Ekahau, I thank you for putting this on. It's always great information and great fun.
Thank you, Jim. That is fantastic. You know, it's interesting to see all of the testing that you've been doing.